Lens aberrations by M.K. Srivastava, Department of Physics, Indian Institute of Technology, Roorkee, Uttarakhand. In the last lecture, we considered chromatic aberration and a spherical aberration. In this lecture, we shall take up the remaining monochromatic aberrations, and these are number 1 gamma, number 2 astigmatism, number 3 curvature of the field, and the fourth one distortion. Let us begin with gamma. The gamma or chromatic aberration is a primary aberration associated with an object point even a short distance away from the axis. You see, away from the axis is the main thing. Its origin lies in the fact that the principal planes can actually be treated as planes only in the paraxial region. They are in fact principal curved surfaces. Look at this figure showing the rays coming from the first principal focal point. The emergent rays naturally are parallel, but the point of intersection of the rays diverging from the first principal focal point and the emergent parallel rays, their point of intersection does not lie on a plane. It is really curved, particularly mainly actually for those rays which are not paraxial. Similarly, in the second figure, the rays parallel rays after refraction, they are focused to the second focal point, but the point of intersection of the incident parallel rays and the refracted rays which are getting focused at the second focal point, their intersection does not lie on a plane surface, that surface is curved. This curvature appears really for those rays which are not paraxial, for the marginal rays. The rays which proceed near the axis of the lens, they focus at a point different from that of the marginal rays. Thus, it appears that the magnification is different for different parts of the lens. If you consider the image formation by different zones of a lens, the paraxial zone or the marginal zone, then the spherical aberration arises due to the fact that different zones have different powers, and gamma, it arises due to the fact that different zones have different magnifications. You see, this figure illustrates the effect of a gamma. The resultant image of a distant point object of the axis is shown in the side figure. The rays in the tangent plane are shown. You see, the chief ray which passes through the center of the lens goes undeviated, and you see the marginal rays, these are the ones which give rise to gamma, a broader circle near the axis and a vertex close to the point P. Let us consider in this figure several askew rays are shown from an extra axial point. You note that each circular cone of rays whose endpoints 1, 2, 3, 4, these are that circular zone of the lens from where the rays are coming, they are focused in a chromatic circle. You see, as the radius of this circular zone decreases, as we come towards the center of the lens, this cone on the image, the chromatic circle, its radius goes on becoming smaller and smaller, and its center moves towards the vertex of the cone. In the limit, when we consider the rays passing through the center of the lens, that gives rise to the vertex of the cone. Now, this case corresponds to a positive gamma, so that larger the ring on the lens, the more distant its chromatic circle from the axis. Now, comma can be eliminated if a lens satisfies Abbe's sign condition. N1 y1 sin theta 1 is equal to N2 y2 sin theta 2. N1 y1 theta 1, they refer to the refractive index, height of the object above the axis, and the slope angle of the incident ray of light. Similarly, N2 y2 and theta 2, they refer to the corresponding quantities in the image medium, on the image side. Now, the magnification of the image is given by y2 by y1, which according to this condition should be equal to N1 sin theta 1 divided by N2 sin theta 2. Now, the elimination of comma is possible if the lateral magnification y2 upon y1 is same for all the rays, irrespective of the slope angle, irrespective of theta 1 and theta 2. Thus, comma can be eliminated if sin theta 1 divided by sin theta 2 is a constant. A lens that satisfies this condition is called an aplanatic lens. Such a lens is mostly used as a front lens of a high power microscope objective called the oil immersion objective. You see, the oil chosen is naturally such that it has the same refractive index as that of the lens. The oil is placed on the microscope slide, which is being observed, and then the lens is lowered into contact with the oil film. And this figure shows an aplanatic lens. You see, all rays from an object at M leave the hemispherical surface after refraction as they came from the point M prime, which is the first image formed by that spherical surface. And this introduces a lateral magnification M prime A divided by M A. Now, if the second lens is added, which has the center of its curvature of its concave surface at M prime, and therefore, this surface is normal to all rays. The refraction at its upper surface of radius n prime times C m prime will give an additional magnification without introducing a spherical aberration, and then the final image is formed at M double prime. Now, this property of the upper lens, however, holds strictly only for rays from a single point M and not for points adjacent to it. That is a limitation with this arrangement. Now, like a spherical aberration, comma is dependent on the shape of the lens, but the interesting thing is the fact that it can be made exactly 0 for a single lens with a given object distance. This is important, with a given object distance. The particular shape it then has is almost convex planar, one side convex, other side almost plane, and this shape, if you remember, is also nearly the shape for minimum spherical aberration, as we have seen in the last lecture. You see, this figure shows a variation of a spherical aberration and also the variation of comma for different shape factors. If you remember, for a shape factor of about plus 0.5, the spherical aberration is minimum, and that is also the region where the comma passes through the 0 axis. So, that is a very interesting thing. At the same time, we can eliminate this comma and minimize a spherical aberration by a proper choice of the radii R1 and R2. Now, we come to astigmatism. Now, if the first two serial sums vanish, all rays from points on or very close to the axis of a lens will form point images, and there will be no spherical aberration or comma. Now, when an object point lies an appreciable distance from the optical axis, the incident cone of rays will strike the lens asymmetrically, giving rise to a third primary aberration known as astigmatism. The third serial sum S3 is not 0. In the case of an axial point, the cone of rays is symmetrical with respect to the spherical surface of a lens. There is no need to make a distinction between meridional and sagittal planes. The ray configurations in all planes containing the optical axis are identical there. In contrast, here the configuration of an oblique parallel ray will be different in the meridional and sagittal planes. As a result, the focal lengths in these planes will be different. In effect, here the meridional rays are tilted more with respect to the lens than are the sagittal rays, and they have therefore a shorter focal length. This astigmatic difference increases rapidly as the rays become more and more oblique, that is, as the object point moves farther off the axis, and is naturally 0 when the object is on the axis. Now, having two different focal lengths, the incident conical bundle of rays diverging from the object takes on a considerably altered form after refraction. The rays in the meridional plane converge at a different point as compared to those in the sagittal plane. Now, this figure shows rays diverging from the point P in the meridional plane constituted by rays P A and P B. They are focused at the point T, while the rays in the sagittal plane constituted by rays P C and P D, they are not focused at the point P, they are focused a little farther away at the point S. The rays P A and P B in the figure focus at the point T, and rays P C and P D focus at a point S, which is different from T as shown in the figure. Now, since at the point T the rays in the sagittal plane have not still focused, one in fact has a focal line which is normal to the meridional plane. This focal line T is called tangential focus, meridional focus, or the primary image. Now, beyond this point, the beam's cross section rapidly opens out until it is again almost a circle. At this location, the image is a circular blur, not very well focused naturally, and known as the circle of least confusion. Moving further, at S, the rays in the meridional plane have now defocused. One again obtains a focal line lying in the tangential plane, and this is called the sagittal focal line or the secondary image. It is in the meridional plane. The distance between S and T is a measure of astigmatism. This figure shows that variation at P1. This is what in the figure was the point T, the tangential image, where the rays in the meridional plane are focused. Then as we move away from it, away from the lens, the bundle of beam opens up a little more, becomes circular, then again begins to close in a perpendicular direction, closes further, and at the point P2 you get the image where the sagittal rays are in focus. One thing should be noted, the secondary line image will change in orientation with changes in the object position, but it will always point towards the optical axis. That is, it will be radial. That is the interesting thing. Similarly, the primary image where the meridional rays came in focus, this line image will vary in orientation, but it will remain normal to the secondary image. You see, this feature causes a very interesting effect when object is made up of radial and tangential elements. The primary and secondary images are in fact formed of the transverse and radial dashes. Let us look at this little carefully. You see, we are interested in forming the image of an object which has got a rim and radial spokes. Okay, after passing through the lens, if we consider here in the tangential focal plane T, this is where the meridional rays have come in focus. This is the transverse image. So, the rim is getting focused, the spokes they are very blurred. But then as we move away to the sagittal focal plane, now in this case we are getting the radial spokes are focused and the tangential rim has gone out of focus. Now, to analyze the origin of astigmatism, one finds that for a point on the axis, when the lens is free from other aberrations, the wave fronts emerging from the lens are spherical, and thus as the wave front progresses, as it moves, it converges to a single point. But when the object is non-axial, quite away from the axis, then the emerging wave front is not spherical anymore, and as the wave front converges, it does not focus to a point, but to two lines which are normal to each other, the meridional line and the sagittal line. Now, somewhere between these two lines the image is circular and is called the circle of least confusion, but it is still not very well focused there. Now, the distance between the tangential and sagittal foci increase as the object point moves away from the axis. Thus, the tangential foci and the sagittal foci of points at different distances from the axis lie on two surfaces. The optical system is said to be free from astigmatism when the two surfaces coincide. They will still be curved, but we shall come to that a little later. One thing we know, these two surfaces, they are coinciding at the optical axis of the system, but naturally that is the axial point. You see, the problem of astigmatism is there as we move away from the axis. And as I pointed out earlier, even if these surfaces coincide, okay, the astigmatism will not be there, but the resultant image surface is in general curved, and this defect of image is called curvature of the field. Now, the shape of the image surface depends on the shape of the lens and the position of the stops. If the primary surface is to the left of the secondary image, astigmatism is said to be positive, otherwise negative. Now, by using a convex and a concave lens of suitable focal length and separated by a distance, it is possible to minimize the astigmatic difference. Such a lens combination is called an astigmat. Now, we come to another defect and the aberration called curvature. The image of an extended plane object due to a single lens is not a flat one, but is a curved surface. The central portion of the image nearer the axis is in focus, but the outer region of the image away from the axis, those regions are blurred, and this defect is called curvature of the field. It is due to the fact that the paraxial focal length is greater than the marginal focal length. Marginal focal length means the focal length for the marginal rays. This aberration is present even if the aperture of the lens is reduced by a suitable stop, usually implied to reduce a spherical aberration, and astigmatism. You see, a real image formed by a convex lens curves towards the lens. You see, the points A and B are nearer the curves towards the lens. For the case of a virtual image, which is formed at a distance larger than that of the object, A prime and B prime, these are curved away from the lens. Now, this figure shows the curvature of the field in the case of a concave lens. Here again the image is formed nearer the lens and the ends A prime and B prime are curved towards the lens. Now, for a system of thin lenses to get a flat image, this is the condition: summation over 1 upon Ni Fi, I summed over the various lens components. For two lenses, this condition reduces to 1 upon N1 F1 plus 1 upon N2 F2 equal to 0. This is known as Maxwell's condition for no curvature. This condition holds good whether the lenses are separated by a distance or placed in contact. As the refractive indices are positive, the above condition will be satisfied if the lenses are of opposite sign. If one lens is convex, the other must be concave. Now, in visual instruments, a certain amount of curvature can be tolerated. It is not very serious. The reason is the eye can accommodate for it. However, in photographic lenses, field curvature is most undesirable, since it has the effect of rapidly blurring the off axis image. Now, the curvature of the field can be corrected for a single lens by means of a stop. Now, we come to the last one of the monochromatic aberrations, and that is distortion. The variation in the magnification produced by a lens for different axial distances results in an aberration called distortion. To be free of distortion, a system must have uniform lateral magnification over its entire field. A pinhole camera is ideal in this respect, for it shows no distortion at all. All straight lines connecting each pair of conjugate points in the object and image planes, they pass through the opening. The constant magnification for a pinhole camera as well as for a simple lens implies 10 phi prime upon 10 phi should be a constant. You see, this figure shows several rays. M prime is the axial ray, then for the ray Q1 upon and Q2 Q1 prime, the angle is phi 1 prime. This ratio is same as for the ray Q2 prime, and the angles are phi 2 and phi 2 prime. Common forms of image distortion in an actual lens system are shown in the figure here. First one represents the undistorted image of an object consisting of a regular wire mesh. The next diagram shows the barrel distortion. This arises when the magnification decreases towards the edge of the field. It is more near the center of the field. And the third figure represents a pincushion distortion corresponding to a greater magnification at the borders, leading to, it looks like a stretched configuration. A single thin lens is practically free of distortion for all object distances. It cannot, however, be free for all the other aberrations at the same time. Now, if a stop is placed before the lens, that is in the object space, the distortion is barrel shaped, more magnification near the axis and less towards the edges. And if a stop is placed after the lens, that is in the image region, the distortion is pincushion type, stretching at the edges. So, that immediately gives us an idea. To eliminate distortion, a stop is usually placed in between two symmetrical lenses, so that the pincushion distortion produced by the first lens is compensated by the barrel shaped distortion produced by the second lens. Projection and camera lenses are constructed in this way. Now, let us summarize these things briefly, all the aberrations we have gone through. See, various methods of correcting for monochromatic aberrations, a spherical aberration and comma we have seen can be corrected by using a contact doublet of the proper shape. Astigmatism and curvature of the field require for their correction the use of several separated components. The distortion can be minimized by the proper placement of a stop in between the components of a lens system. Now, let us see this problem in totality, and keeping in mind different types of optical instruments. The lens may be affected by as many as 7 primary aberrations, 5 monochromatic aberrations as we have seen, and 2 chromatic aberrations, longitudinal and lateral. Now, one might therefore wonder how it is possible to make a good lens at all, when rarely can a single aberration be eliminated completely, much less all of them at the same time simultaneously. You see, the good usable lenses are nevertheless made by the proper balancing of the various aberrations. You see, the design is guided by the purpose for which the lens is to be made. You see, that is the main thing, where the lens is to be used, that guides which aberrations are to be eliminated or minimized or properly to be taken care of. In a telescope objective, for example, correction for chromatic aberration, spherical aberration and comma are of primary importance. On the other hand, astigmatism, curvature of the field and distortion are not as serious, because the field over which the objective is to be used is relatively small. For a good camera lens of wide aperture, wide angle, the field situation is almost exactly reverse. Okay, so I think with this we have come to the end of this lecture series. Hope you have liked it. Thank you.